Welcome to Hocking College, Lab 1102. This is week 6, day 2. We're going to continue talking a bit about sampling today. Let's start with something that, as soon as the slide changes, we will start with something that there we go. Something that I meant to cover Monday. Yeah, Monday. Today is Thursday. Here in the quarantine land, everything runs together. Something I meant to talk about Monday is aliasing. It's basically anytime your sampling rate, number of samples, whatever, manages to hide or misrepresent something. A great example of this is you can see it in anything that's on film that's rotating. So if you watch old Western movies, sometimes it looks like the wagon wheels go backwards because of the recording rate for the video catches spokes at the wrong time, and so it looks like it's rotating backwards. You can see it on some car shows now. So if you watch Top Gear, for example, and you watch the tires as they're being filmed, there's spots where it appears they're going backwards. If you haven't seen that, I did find this nice video on YouTube that will take a couple of minutes to watch. You get a good example of what aliasing can do. I think it's a fairly quiet video, so mostly you hear the airplane, because really all we care about is what you see in this. I didn't hear any words. You can see the plane, it's rotating. Here's it speeds up, and it will get to the point where it's rotating faster than that. There we go. Now it looks like it's going backwards. Then it's forward and then backwards again. As it's rotating a little bit faster than the film speed, it looks like it's going backwards. And depending on the engine speed in relation to the film speed, it can look like it's going forwards or backwards. You saw for a moment there it even looked like it was still, is that everything synchronized just right for a frame or two. So we don't really need to watch all 2 minutes of this to really see what the effect is. So I'm going to go ahead and stop that. So yeah, that can happen with your tests and your data if things are not set up right. It's more common in things where you've got some sort of continuous sampling going on. If your data acquisition rate where it's talking to the computer is wrong, but it could still happen anytime you've got something that's cyclic. If you're sampling at the wrong time in that cycle, or if you're not sampling often enough in that cycle, you might look like things are going backwards or staying still instead of doing what they're supposed to be doing. Okay. Wow. All right, I'm going to pause for a second and repair this slide. Just a moment. Okay, there we go. Oh, sorry, just a moment again. Okay, there we go again, for real this time. It's still not exactly pretty, but that's apparently what I get for doing some of the creation in one program and then working from another. All right, so let's move on to separating an analyte from the interference. Sometimes you have to, you can't account for or correct for the interference in the test, and you have to do something to separate the analyte and the interference. You need some sort of difference in chemical or physical properties to do this. So A density difference you can do by using a centrifuge. The heavier stuff goes one way, the lighter stuff goes another. They separate blood this way all the time. You can a difference in boiling point lets you separate things by distillation, etc. So the limits are if you fail to recover all the analyte in one phase or remove all the interferent from that phase, then you've got a problem. They measure this with either the recovery or the separation factor. Both of these are the ratio of the concentration after your separation to the concentration before. So your separation factor is the concentration of the interferent after the separation in the portion that you're going to measure to the concentration of the interferent before separation. And the recovery is just the same thing, except it's the analyte. So if your separation factor is, let's see, we would want a low separation factor, then, that would mean there's not a lot of interferent left in the portion that you're going to be sampling. You want a high recovery factor. You want your recovery factor close to 1 and your separation factor, unless I'm misremembering this, you want your separation factor to be as low as possible, unless I'm misremembering and the separation factor is also with the component that the interferent is supposed to go to. Let me pause and... Okay, I've double checked that. It is correct. You want the separation factor to be low. The book goes so far as to say you want it on the order of 10 to the minus 7th to be a usable separation, that it won't be interfering with your tests. Anytime you're doing something like that, you're introducing the chance for errors. Of course, you're doing something. There's always the chance that you'll mess up, but there's also, you're never going to get 100% perfect separation. There's going to be some interferent left. That's still going to cause something. Some of your analyte is going to go away with the interference. Hopefully as low a percentage as possible, but still some of it goes that way. So there's a little bit of error that comes in from that. Again, there's a nice error defined for this. It's what you've got after the separation minus what you would have if the separation was perfect and you recovered 100% of your analyte over the actual amount. So how they define that error. Oops, I'm in the wrong. It's the right window. There we go. All right, so let's talk a bit about separation techniques. There's a lot of physical. As I said, you need some sort of physical or chemical difference to do the separation. So you can separate things based on size by using filtration, dialysis, things like that. Anything where you've got some form of physical barrier that one component passes through, the other component can't. And some of the stuff that should pass through might get stuck, caught on the filter or caught against the things that can't go through or something like that. There's still, it's never going to be 100%. As I mentioned, with mass or density, you've got centrifuging, complex formation. So if one component or the other, ideally the interference, if you can react it with something to make it not interfere anymore, that's what they refer to as masking. So you're reacting it, and all your interferent gets reacted and is no longer active in terms of your test, then you've masked its presence and you can get a good reading, ideally. Change in physical state, so things like distillation, again, you're changing the physical state from a liquid to a vapor. If your boiling point is different enough, you can get a fairly decent separation. Recrystallization, you're going from a liquid to a solid with one phase and not the one component, not the other. Um, things like that. Those can also be used for separation. Excuse me. Change in chemical state. Similar, you react sort of like with masking. You react it with something that makes it um, more volatile, so it evaporates, or less soluble, so it precipitates. Something like that. Maybe you can electrodeposit one component and not the other. Um, Last thing we've got is partitioning between phases, and we'll talk a bit about liquid-liquid extraction in a moment because that's a good example. Chromatography is another one, and we'll talk about chromatography a bit in a few days. Basically, you've got some sort of media where one component moves through it faster than another. And I will. There's a great at-home kids science experiment that qualitatively, meaning without numbers, or shows how this works. Um, and so I'll make sure we've got that set up beforehand. So liquid extraction. Basically, you need two liquids where the liquids don't mix. They're like oil and water. They're non-miscible. Um, immiscible, yeah. So you need liquids that are immiscible, like oil and water. They're not going to mix. Um, and either your analyte or your interferent needs to be a lot more soluble in one than the other. So you stick them in a separatory funnel like this. You close off the little valve at the bottom. Um, you've got your sample in. You add the immiscible liquid that one component, not the other, is highly soluble in. Shake it up really well. I haven't done this since organic chemistry in college, so I don't remember the guidelines for how much shaking needs to happen. Um, so you shake it up very well, and then you let it sit and settle back out, and let those two liquids separate. And um, might need to repeat the shaking process a few times. Like I said, it's been a few years, so I'm not positive. Um, then you very carefully open the valve and remove the denser liquid. Um, and your analyte should be in one phase and your interferent should be in the other, and you can test the appropriate phase and go on your merry way. As the book said, this is a fairly common, important part of analytical chemistry, or it has been. So this is something that it's not out of the realm of possibility that you can see and be doing. So I wanted to make sure you saw the glassware that goes into this. They do spend some time in, let's see, this was in section 7.7. They also, if you want to look at section 7. In section 7.6, there's some stuff about solid liquid extraction, or solid phase extractions, and continuous extractions. We're not going to go into that. You should get what you need to from that in follow-up courses. What I want you to get out of this and understand is that you're using a physical or chemical difference between the analyte and the interferent to do a separation. There's got to be a difference, and it's got to be large enough to be meaningful. Um, and if that's the case, you can usually separate them by exploiting that difference. You know, if the density is different enough, you can put them in a centrifuge, and the two components will the components will separate by density. If your boiling point is different enough, you can boil it, and the more volatile component will boil off before the less volatile component. Um, and then you can recondense the volatile component, and that's how you get whiskey. Um, um, a lot of these separation techniques, in addition to being useful in the laboratory scale like this, are also quite important on the industrial scale, and from the small industrial scale, like distilling ethanol to make dis- distilling fermented grain to make whiskey, or distilling to separate crude oil components into gasoline and diesel fuel, and things like that. Um, and a lot of the continuous extraction things as well. Recrystallization is pretty common in pharmaceutical to separate out the compounds you're interested in recovering from whatever process you're making the pharmaceuticals with. That's a fairly common separation technique in pharmaceuticals, as is some of the chromatography techniques. So these are common both in the lab and industrial scales. All right. Finally, we have pre-concentration, which is basically a separation technique that lets you increase the analyte concentration. So if we're moving the analyte from one phase to another, and the phase we're moving it to has a lower volume than the phase we're moving it from, then we're increasing the concentration. So if we've got a sample where the concentration of the analyte is expected to be too low to measure, or almost too low to measure, or too low to measure very well, then we can do some form of pre-concentration to increase that concentration and get it to a range we can measure. And as long as we know enough information about the volumes and recoveries, we can do that and account for it and come up with the concentration in the phase it came out of, where our sample was. Okay, that is what I had for new material today. Again, in the lecture during class time, we'll go through this, and we'll have time for questions, and I'll do a couple of sample problems again. Oh, that's right. The other thing I wanted to show you all was where the recordings are for the class sessions. So let me get to student preview mode, so I'm seeing some things the same way you will. Start preview. It'll just take a minute or two to load here. Okay, still loading. Okay, there we go. So there's the join session where we go to get into Blackboard, to the collaborate session. If you click here on the more options, you go to view all recordings, and wait for it to load. And there they all are. I don't know why. just force that to an early range to try to make sure we see everything. There we go. So they are all there. There we go. So yeah, that's where the recordings are. And hopefully I will see you all. And don't forget, you can still do the homework and participation portions at any time. You can redo the homework if you're not happy with your grade and get a better one. Please just email me or message me in Blackboard and click the send an email and let me know, and we will get them updated. I updated last April 29th in the morning. So I hope to see some of your grades going up soon. Thank you. Bye.